Welcome back, everyone. We'll start the second part of the morning session with Anand Kumar from IIT Kanpur. Please.
Hi. So, thank you. Well, thanks to Abhishek and other organizers for inviting me to give this talk. I'm not really a quantum trajectory person, but we do coherence and other stuff in the quantum optics domain. And those are the few things, maybe I can go that side. I'm just kind of planning to talk about. So just a brief as to, I have a quantum optics entangled lab. I'm essentially an experimental person. And these are the things that we do in the lab. Just study of coherence in the classical and quantum domain, using the correlations of light for imaging through scattering turbulent medium, quantum state reconstruction through correlation function measurement, orbital angular momentum of photon, its detection, generation, entanglement, and application, and also some exploding connections between coherence and quantum entanglement. So what I'm going to talk about today is essentially this part, the connection between coherence and quantum entanglement. Since it's primarily a theory conference, so what I have planned is just to have some theory work that I have done. These are mostly experimental that I'll try to kind of present here. So here is a brief kind of outline, some basics of coherence, and then two-photon interference and coherence and how it works out, especially also in the context of experiments related to entanglement, and that brings me to exploring connections between multi-particle coherence, multi-particle entanglement, or mostly I'll be focusing on two-photon coherence in the photonics domain. And when we talk about entanglement generation, how do correlations kind of transfer from one particle system to two particle system, or one photon system to two photon system? And finally, some modern applications that people are actually using these correlations in, especially in the quantum metrology and quantum imaging. So with that, what is coherence? So coherence essentially is the degree of order in a random field. And what we mean by that is if you take any typical light source, it consists of several emitters, which are normally completely uncorrelated. And when you have light coming out, for example, the light bulb, the different emitters are completely uncorrelated. So when the light comes out of such a source, it may get some correlation after a while. So then you ask the question, how does the field vibration here connect with the field vibrations kind of over there? That is a generic question in any coherence theory or correlation theory. So the way you answer that question is kind of pick up light from this place and this point, and then superpose them at some other screen. This is a typical Young's double slit kind of setup. So if you look at the intensity of light at any point, if you look at any point in this observation plane, the amplitude there, of the field amplitude there, will have a component coming from this point and a component coming from that point. Of course, there's a factor because there's a loss, and there's a diffraction and so on. But this is generic structure that the field here is a superposition of field coming from this point and that point. And based on that, when you calculate the intensity here, what you find that intensity has a term which is the intensity coming from this point, this one intensity coming from this point, and if both these points or slits are open at the same time, then you will get this cross term. Now this cross term has this function gamma, which essentially contains the correlation, information about the correlation between these 2 points. So by measuring this intensity over there, you try to find, experimentally, you try to find what is the correlation over there. That is what we do in kind of correlation theory or coherence theory. This one is called the intensity, and this one is called the degree of coherence function, and that is how it works. And just to get some intuitive understanding of what is degree of coherence, so if it's a very high degree of coherence, what you will see is a very high visibility interference pattern. That means the change of intensity up and down. So that's highly coherent. If the visibility is not as much, you'll call it partially coherent. And if it's almost kind of flat, then you call it nearly incoherent kind of light. Here the coherence is in the space domain, so we mean the spatial coherence and this space point and that space point. In that sense, it actually. Okay, so as far as coherence is concerned, there is hardly any difference between the classical wave mechanics and quantum mechanics consisting of wave functions. And what I mean by that is that if there is no randomness in the system, classical wave theory, then we refer to it as field. In quantum mechanics, we refer to that as a pure state. A field can be represented in terms of a Fourier transform, like a time domain signal. You can represent that as a frequency domain signal in a Fourier representation, Fourier transform. Similarly, in the quantum domain, we write as a pure state, and that can be written as a superposition of state in the other domain. This is a representation of signal in the space that can be written as a Fourier transform signal in the spatial frequency domain. You can have a similar representation in quantum. Here is an example of a field in the, let's say, some angle basis, which is periodic. So this time the Fourier is discrete instead of being continuous. You can have similar representation in the quantum domain. Well, e to the IL5 fields are, the modes are quite important because this represents like the vortex mode or the orbital angular momentum modes of single photon field. Now, when there is randomness in the field or for random processes, we don't use fields, we have to use correlation function. In classical, we use the correlation function like that, V star V. And in quantum, we use the mixed state, that is the density matrix. This is the ensemble average, the same ensemble average over there. And so the correlation function in the classical field, classical coherence theory, and the density matrix elements, they're pretty much the same and should be treated the same here. So that's the parallel I think I'll be kind of referring to throughout the talk. So when we talk of interference, whether it is one particle interference or multi-particle interference, the best way to describe this is this one-liner by Dirac, that a photon essentially interferes with itself. What it means when we have the high intensity classical field, then the interpretation, okay, we divide that into two, part of the amplitude goes there, part of the amplitude goes there and gives me interference. But when we come to a single photon level, then that interpretation doesn't work. Because let's say if I have single photon, now it comes to the beam splitter, it has to decide whether it can go this way or it can go that way, because it can't divide itself. So it can go this way or it can go that way. Now the interference takes place if these photon paths are mutually coherent in the more classical language, or in the more quantum language, you'd say the photon paths are indistinguishable. So only then, so indistinguishability and mutual coherence is pretty, again, very much a similar concept or almost the same. And that's how the interference happens. And if you try to understand this is mind-boggling. So the best way is that, okay, photon interferes with itself. Now, more at the math level, so when you have this kind of setup where you have either a photon or a field going through this kind of interferometer, which provides two different alternative paths for it to get to the detector. So here you have one path, which is that, okay, photon can go this way, second path, photon can go this way, and the way the interference is described, whether classical or quantum, is like you open it up, just like this path diagram. You say, okay, L1 is the path that the photon had to travel from the source to the detector in alternative 1, and L2 is the path that the photon had to travel from alternative 2 from the source to the detector. And this delta L, the difference in the path length is L1 minus L2. And if you just derive the intensity over there, then you find it's a very similar structure as so for the Young's double slit. There's the first term which consists of the intensity of this arm, second intensity, or if I'm doing photon, it will be the photon probability, probability photon arriving at the detector or the photon detection probability. And then you have this cross term over there. So this gives me a necessary condition for interference, that this gamma function, which can be between 0 and 1. So it depends on this delta L. So as long as this delta L is less than the coherence length of the light field, then we'll have interference. And just for the visualization, you can imagine this kind of wave packet. This is not the actual wave packet, but like the coherence packet, the size of which is like the coherence length. And then when you change the path length of this interferometer, then it's like they're going past each other, and as long as overlap is there, there will be interference. So just a way of kind of visualizing how the interference in the time domain happens. And the high visibility near delta L equal to 0, that's when you have the full interference, full coherence. And the size of this envelope is kind of like the scale of this coherence length. Okay, so this is kind of all known as how we understand the classical interference, and we can also understand the single photon interference. Now, before going to the two-photon interference, the one process by which you actually do generate two-photon fields or entangled two-photon fields is parametric down convergence, a nonlinear process in which you absorb one photon at omega 1 and emit two photon omega 2, omega 3. Of course, omega 2 plus omega 3 has to equal to omega 1 for energy conservation. The two emitted photons are called signal idler. And so in a lab setup, this is the situation. You have a classical pump field, high intensity. This is a very inefficient process, chi2 second order nonlinear crystal, and thereby you generate two entangled photons, signal idler. There are two length scales associated with these photons generated. One length scale is associated with, typically these photons, the signal idler, are much broader frequency bands they have, and the pump has a much narrower band. So correspondingly, these photons have a much smaller coherence length, and the pump has a much larger coherence length. And if you talk of the order of magnitude, the pump can be in tens of centimeters, while these signal idler are like 100 microns or so. Now, I just want to go through some of this very famous two-photon kind of interference experiment. Some of it may be familiar to this kind of audience. So one is this Honger-Mandel effect, came out in 1987. Very simple experiment. You have this entangled photon from PDC. You combine them at a beam splitter. Now, from this balanced position, which means this path length is exactly equal to this. If you move this beam splitter, then what you find is that the coincidence count rate, the joint probability of detection, gives you something like this. So when x is 0, the conditional probability is 0, and then you have this kind of structure. This is called a Honger-Mandel dip. So when x is 0, the interpretation is there is no coincidence. That means both the photons go either this way or that way. So in 1987, it was interpreted as what's called the bunching effect, that when two entangled photons arrive at a beam splitter, they kind of bunch together, either go this way or that way. Now, later in 96, it was shown that the bunching interpretation may not be absolutely correct, because what they did, they introduced a delay before the photon got to the beam splitter, just to make sure that they are not arriving simultaneously at the beam splitter. So there is a delay between when the photons arrive, so there's no question of kind of them bunching. And then they compensate for this delay afterwards through this polarization trick, and then they see exactly the same effect. So this Honger-Mandel, which was thought to be giving rise to the bunching interpretation, this shows that yes, you can have bunching interpretation, but that is not the complete story. This experiment is induced coherence experiment. This came out in 1991. This is also sometimes referred to as Len Mandel's like wow experiment. This is really incredible. So in this one, you have a pump field, you divide that into two, and there are two different down converters. So if the pump photon goes here, it down converts here, and then the way it reaches detector is like this and that. But if the photon comes here, then it down converts in this crystal, then it can go to the detector like this and that. The assumption here is that the photon either down converts here or there, not in both. Now within this, what Mandel showed that if you don't look at coincidence, just look at the intensity here or the single photon probability over there, you do see interference as a function of this x. This was very, very mind-boggling, because if I see if I see interference in this detector, that means the photon could have come like this or like that. These are red photons, and their coherence length is about 100 micron. But the path length difference between this and that is about 15 centimeters. So there's no way these two can interference the way we understand kind of how interference works. So Mandel actually introduced this idea of induced coherence, that well, since these photons are entangled, when these two idlers are exactly aligned, then there is a new kind of coherence that gets induced between these two, and hence we see interference. Then there was this experiment from Zeilinger's group in Vienna. This was even more mind-boggling than this. Now in this experiment, you have this pump photon coming in, it down converts either in its forward pass or backward pass, either or, not in both. So now if I look at just the intensity here or the single photon detection probability here, what I find that the photon can go like that or like that. Again, the path length difference between this and that is 15 centimeters. The coherence length of these photons are about 100 micron, but we do still see interference when we move this mirror. But in this experiment, you saw interference even when this mirror was moved. Now this induced coherence explanation doesn't work here, because if I'm moving this mirror, then I'm not moving this mirror at all. So if there is path length difference, that remains constant. So by moving this mirror, why should there be an interference at all? But they do see interference, and it was pretty mind-boggling at that time. So these are the different kind of two-photon interference effects were there, and lot of different explanation as to why this kind of effect happens. Now there's one way of kind of putting it all together in kind of one coherent theory, and that which is kind of pretty much consistent with Dirac's way of explaining things. And this time it can be like a two-photon interference itself. So I'll just go through this. So I'll take this as a generic example of two-photon interference, but this can represent like any interference scenario. So in this case, I have two different situations or two different alternatives by which this photon can get down converted, and the down converted photons can reach the detectors. So in this one, you have this pump photon coming in like this, just goes like this, comes back and gets down converted in its backward. And in this case, it is in down converted to the forward pass and then kind of goes back. So now you can simply write this path diagram for these two alternatives, and then the midpoint of these alternatives you can call the difference, you can call delta L, and these asymmetries in the path length of signal idler one can call the path length asymmetry, and correspondingly delta L prime. And if you just work out the math through this Glauber's theory, 1963 quantum theory optical coherence, what you find is that the joint probability detection has this structure. This R1 is the probability joint detection probability from if you had only this alternative. R2 is if you had only this alternative. And if you had both, then this is what you get. And now you have two different coherence terms, gamma prime delta L and gamma delta L. So although you had 6 different length parameters here, but you could write this RSI, the coincidence probability, in terms of just this delta L prime and delta L. So the correspondingly, well, if you put this R1 equal to R2, that this has a simpler form. And so correspondingly, this time the necessary condition for interference you get is that delta L has to be less than the pump coherence length, and delta L prime has to be less than the signal idler coherence length. And with this actually kind of unifies all that different experiments and different effects that you see with two-photon. So now if I go back to Honger-Mandel effect, which is this. So this time I can write it like this. This is one alternative, the second alternative. And then in terms of delta L prime, delta L actually becomes 0, delta L prime is 4x cosine theta, and as you change this beam splitter position. And as a result, since delta L is 0, this is 1, there's nothing here, and then you get this dip profile without any interference pattern. If you come to this postponed compensation experiment, in this experiment was essentially same as Honger-Mandel, except the delta L is equal to D, which is the fixed thing here, and it still doesn't depend on the X. And so that is the expression you get this time. So if you change X, since this is fixed, it doesn't change, you still get the Honger-Mandel dip. Regarding these other like wow effects that you see in the single photon detection, again, this can be kind of explained just by using the very classical probability theory, where a joint probability or the individual probability can be represented in terms of sum of joint probabilities. If you have two events, X, Y, J, then Px is sum of the joint probability of P, X and Yj, where Yj is the kind of set of mutually exclusive events. So if you bring it to this entangled photons, what you have in this case is that if I have singles rate, this will essentially be equal to the coincidence count rates, where Yi are all the position where the entangled partner can actually go to. So with that, if you take this induced coherence experiment, I do this diagram like this. So in this case, delta L prime, delta phi go like this. That's the expression for RAB. That means coincidence between A and B that I get. Now, if I look at the one single photon count rate, what do we have here? Now, if a photon arrives at RA, where is the other place that the partner photon can go to? And if you check this B, the DB is the only place the partner photon can go to, because if a photon arrives here, that means it could have come like this, partner photon will go like this, or the photon could have come like this and the partner photon will actually go here. So if a photon arrives here, its entangled pair can only go there. However, if a photon arrives here, then its partner can actually go to DA as well as to DC. So the photon count here will be equal to just RAB, but the photon count at B will be equal to RAB, RBA and RBC. So we already know what is RAB. So if you just calculate RBC, very same, almost the same expression, except this is minus, this is plus. And if you plug that in, you find RA has this interference pattern while RB is just a constant. And this is how this can actually be explained. And just to give you intuition, just like we have for the this case, there's a very similar intuition that also works for the two-photon case. So you can think of these two photon having this one big coherence wave packet that corresponds to that of the pump, and these smaller wave packets. And if I'm to simulate the Hongo-Mandel case, but delta L prime is 0, that means there's no asymmetry between these the smaller kind of ellipses. And so you have this kind of overlap, and then the interference is pretty much exactly the same as what we see in the classical case or one photon case. But if you come to the other extreme where delta L is 0 and delta L prime is not, then since delta L is 0, what we have, there's no overlap changing between these blue ellipse, only there's an asymmetry between red, and that's what gives me the Hongo-Mandel interference. Okay, so now one thing in this one, this particular setup, if you look at this delta L and delta L prime, what we find is that in this particular setup, if you move both these mirrors in the same direction by same amount, then you see this nice interference as far as coincidence is concerned. But if you keep this delta L fixed at some point, and after that start moving these two mirrors by equal amount but in the opposite direction, then that amounts to changing only delta L prime and not delta L. And that actually gives you this Hongo-Mandel effect. And depending on which L you fix things at, and then change delta L prime, you can either get a dip or a hump. So this is actually a Hongo-Mandel effect without even a beam splitter. So there's no question of photon arriving simultaneously or later. So you can have Hongo-Mandel type effect even if there is no beam splitter. In fact, not only that, at least in this setup, if I look at the coincidence singles count rate here, if the photon comes here, this partner can only go there. So singles here is equal to the coincidence essentially. So whatever you see in singles in this experiment, coincidence in this experiment is the same thing that you see in singles. So you not only see in coincidence, but you also see the Hongo-Mandel type profile in singles counted or the intensity measurements. So okay, so now this is how the two-photon interference experiments can be explained in this. But now what you have in these experiments is that you have a pump and that has some coherence, and then you generate entangled photons through that, and then you interfere them. Now, if you just look at these intensity coincidence intensity expressions, you find this is always there's a coherence function that depends on delta L, another coherence function depends on delta L prime. Now, this coherence function, I haven't shown you the exact form, but the functional form of this coherence function is exactly that of the coherence function of the pump. So this actually shows that although the pump is kind of gone after it down converts, its coherence function still survives even after down conversion. So it's the coherence actually gets transferred in the two-photon field, and that has some application, modern application, which I'll show towards the end. So temporal coherence properties of the pump, do get transferred to the entangled photon field. And if I'm looking at it in the sense of a two qubit time in entangled state, then you find that if the density matrix are this kind of structure, there's a very nice connection between entanglement also, so and that is the concurrence of the state becomes equal to the visibility of the interference pattern you will actually see. This is a very direct relation. And that visibility is of course connected to the degree of two-photon temporal coherence. Now if you go to the space domain, we can work out a very similar theory. I will skip this part. But what we find even in this case, what we find is that the coherence function or the degree of coherence function has the same functional form as whatever was the pump here. So the special coherence properties also do get transferred to the two-photon field. And again, you have the same kind of conclusions here, that if you make a 2-qubit state, spatial 2-qubit states out of these photons, and if the state has this kind of structure, then you have very direct relation as the concurrence of this 2-qubit state becomes equal to the visibility of interference pattern that you actually will see. Of course, this doesn't generalize that even for a density matrix which is kind of general, do we have this expression? The answer is no, but maybe there is bound, but not this direct relation. Of course, this is again connected with the two-photon. Sorry, this is not temporal, this is spatial coherence. Now, you can see similar effects in also polarization. So polarization is when we think of polarization as a two-dimensional basis, I can have a density matrix 2 by 2 that represents polarization. And the degree of polarization, that actually is a basis independent way of quantifying polarization coherence, which is given by this. And then you ask the question that, okay, through this pump, I generate the signal idler, and they go through some process, and by that I can generate any 2-qubit state, generic 2-qubit state. I'm not showing the actual experimental setup for that, but it can be any 2-qubit state that I can generate out of here. And then I ask the question that this 2-qubit state that I have gotten generated here, and if I quantify that through the concurrence entanglement, is there any connection between this degree of polarization here and this concurrence that I can generate of this 2-qubit state? So the answer is yes. There's a very nice general bound that you find that the concurrence of this state has to be less than 1 plus p by 2, where p is the degree of coherence polarization, polarization coherence of the pump field. Now, if you restrict it for the two-dimensional state, the way where the density matrix has this kind of form, then you find that concurrence gets limited by just the degree of coherence. So whatever is the degree of coherence, degree of polarization, that will be the maximum value the concurrence can actually have. So here one consequence you see that even when the degree of polarization or coherence is 0, you can still have concurrence up to half. So if completely unpolarized light can still generate 2-qubit state with concurrence up to half. Okay, now this was a polarization which is two-dimensional state. We also wanted to kind of do this for higher dimensional states since of working with orbital angular momentum and so on. But then you realize that this degree of polarization way of defining it, this works only in the two-dimensional state. For higher dimensional state, things are not there that way. But now we can have this intrinsic degree of coherence kind of defined. This is also called the purity of the state. And then this formula generalizes like this, that n trace rho square minus 1 by n minus 1. And that kind of gives you the intrinsic degree of coherence. Again, this is basis independent. And for continuous barrel, it can just be the trace rho square. It gets connected to the 2-point correlation function and also with the Wigner function. And then the same formulation you can also have for the 2-qubit state. You can actually define what's called intrinsic coherence of a 2-qubit state, which is given by this. And there's a very nice kind of connection between kind of Bell parameter for the entanglement verification. We know that Bell parameter S has to be less than this 2 root 2. But you find that if the qubit state has this intrinsic coherence of p 2 by 2, then that limits what is the maximum value of S you can have. So for example, if for maximally, if p is 1, this p 2 by 2 is 1, then you retrieve your 2 by 2, S equal to root 2 by 2 kind of bound. This also has a connection with concurrence also, although in terms of an inequality, that if I have this 2-qubit intrinsic coherence like this, and the intrinsic degree of coherence of one of the photons are like this P2, then there is a relation like this between concurrence of the state and the other quantities, and that also gives me criterion for entanglement. Now, the hope here, which is, I have not done it yet, but that is kind of unfinished program, that if we can have multi-particle coherence get connected with multi-particle entanglement, because if I can do that, I know how to measure this multi-particle coherence, but measuring entanglement sometimes can be very, very difficult. But if there is a connection, maybe there is a ease as far as measurement is concerned, experimental. Okay, so with that, maybe I have a few minutes left. So I just want to quickly give what are the modern applications in imaging and metrology of all that, these two-photon coherence that we have seen. So this Hongo-Mandel effect, where you have this, so I'm going back to the old-fashioned bunching interpretation. So you have bunching interpretation, both the photons either come this way or that way. That gives you a noon state, and that can be used for what's called a quantum lithography. But before I go quantum lithography, just quickly, in the classical lithography, how it works is that you have a photon or a beam of light, divides that into two, then you combine them, almost near grazing incidence, and you write a pattern on that. And this pattern, which is it is the IKX, I minus IKX. Let's say for a given wavelength lambda, it goes as 1 plus cosine 4 pi x by lambda. Now, if you bring in these two entangled photon from Hongo-Mandel, so you have this two photon, gives you Hongo-Mandel, so either two goes this way, two goes that way. And in that case, if you calculate the intensity of a two photon detection, then for the same lambda, same wavelength, you get twice as many fringes. And if you can have n such photons, which is called the n photon noon state, then you can have n times as many fringes. So that is the idea of quantum lithography. This is a more modern application, this quantum imaging with undetected photon. This is from Anton Zeilinger's group. This is actually, in principle, same as this Mandel's 1991 experiment. What you see in this experiment, you have these two photons generated from this crystal. One is this red, one is this yellow. Now this red photon goes through this object over there, yellow photon, and then the red photon that goes through the object actually gets dumped. And this yellow photon that never sees the object now goes to the detector and you detect them. So, and then that's how the imaging is done. So the photon that actually saw the object was never detected, but you still are able to image. And that's the quantum imaging with undetected photon. This had another extension, very similar idea of the induced coherence. But this is for quantum image distillation. So you have a noisy image and you have an object. Here you generate the entangled photon. I'm kind of skipping the details. You see there's a red one, there's a green one. Green one goes to the object, but this green one never makes it to the detector. This red makes it to the detector, but you're still able to do the quantum image distillation. So this is the image, this is the noise. If you put together, it looks like this. But through this image distillation, you can actually recover the object. So that's the image distillation, and this works even when the noise is 10 times more than the signal. So that's the quantum image distillation. This one, as I was saying, so this is 23. This is not in parametric down converter. This has been done in vapor cell, rubidium vapor cell, and you still have this one photon coming in, giving you two entangled photon. Now they have shown that the correlation in the pump you can use for encoding. So you can encode something into the pump, and after this down conversion or the four mixing, the pump is gone, but you can still recover the correlation through these photons. And in this case, the correlation was an image like this, and that then they were actually able to recover it through the correlations of the two photon. Finally, this is the very recent work. So the adaptive optics imaging with entangled photon. Now these entangled photons are very tightly correlated in it's a position basis here, momentum basis, and that you can use for doing adaptive optical correction. So for adaptive optical correction, especially in astronomy, you require like a guide star. But here, even without a guide star, just by utilizing the correlation of the two photon, you can actually correct for the aberrations in the wavefront without requiring any guide star. So I think this is it. But since I'm here, I'll just this is just a quick advertisement. So we are part of this national quantum mission where we are doing this design and development of quantum entanglement enhanced imaging system. And several features as part of that, we want to develop entangled photon sources customized for imaging, developing these entangled measuring schemes, doing imaging protocol, and then quantum benchmarking. So we have a team of almost 8 faculty members. I'm the lead PI. We are looking for postdocs and PhD students. So if you're interested, do let me know. Thank you for your attention.
Time for a few questions. Maybe I'll make a start.
Yes.
I was curious about you were describing these relations between the concurrence as an entanglement measure and the visibility and this specific type of coherence, which was I think, purity measure effectively. Are either of these also entanglement measures, or you're really just using them as bounds?
So concurrence is well established. So I was using concurrence in the context where we can make the 2-qubit state, either in the spatial qubit or the time-being qubit. And in that case, is a direct relation that you actually get. When there's a very generic density matrix, I don't have that direct relation, but for the two-dimensional density matrix, there is a direct relation that you get.
So this is a sort of specific case. I guess that makes sense, because generically, maybe the purity doesn't give you a lower bound like this.
Yes,
yeah.
yes, yes.
Cool.
Yes.
Yeah, hi. Thanks for the nice talk. So, in a related questions, are the states mixed? Like, is there a reason why you need to calculate, measure concurrence rather than say linear entropy or something?
Concurrence is almost there as a formula. So if you do linear entropy, I think for that particular 2D states, there should be, because all these entangled measures are kind of connected anyway. So if there is but concurrence basically becomes equal to visibility. I have not tried if linear entropy also becomes equal to the visibility, but visibility is what you get in the experiment, and that actually is concurrence in that case.
But these are all pure states that you're...
No, mixed state.
These are all...
Yeah, it's just a restriction of density matrix that it can only have 2 diagonal elements, not all 4. If there are 4, then I don't have a connection between, well, if there are even 4, but only 2 off diagonal, there also it works with one kind of additional term. But for the 2D density matrix mixed, you do have concurrence equal to visibility.
Yeah. So let me ask you one thing, maybe not connected to your talk, but I know you also work with hyper-entangled states or higher dimensional entanglement. So in those cases also, like, is detection of entanglement simple or?
No, because there's no quantifier like that for the mixed state for those high dimensional. I mean, not that I know of. Yeah. There are these inequalities for as a witness. And then you can have inequalities, but there's nothing like quantifier just as concurrence goes from 0 to 1 for this high dimension, at least as I know. So
thanks.
Further questions? Yep.
Yeah, it's a similar question as Himadri. So from this down conversion, the pair that is produced typically in a mixed state or a pure state?
I mean, you can now people are working with mixed state also. Typically, what you do, or at least when people were doing Bell inequality measurement, the aim was to generate as pure as possible. And since the laser you are using is typically very pure as far as space-time polarization is concerned, so very high purity states you get. But you can also pump the down, which is what I was showing the other case. You can also pump the down conversion with the light which is not pure. So it is a mixed state. Pump light can be mixed state, and in that case, the light that you get out down convert light, that is actually mixed. And what you find is that the degree of mixedness of the pump basically carries over to or decides the degree of mixedness of the entangled photon.
So it's easy to produce either mixed or...
Easy part, one can produce, yeah. Experimentally, yeah, I mean, there are challenges, but one can produce it, yes.
Okay, and the other question was, is it also possible to do like tomography? Is that what you did, like, and find the
So
density?
if I could do tomography, tomography is very difficult. So two-dimensional perfectly fine, but higher dimensional tomography is difficult. But finding a visibility or interference pattern of finding visibility is much easier than doing tomography. So if I could do tomography, then I can directly calculate the concurrence. But that usually is very difficult, and even if you do, a lot of error actually will be there. But if I could directly calculate the visibility, that will be with very high fidelity. And for that, in those cases, the concurrence calculation will become a very high fidelity.
So Anand, just a kind of, again, a slightly broader question. So because there is this there was this back and forth in imaging, which was kind of more or less the last time that I paid attention to this, this kind of stuff, where entanglement was useful and then it was not useful, and thermal correlations from Bob Boyd and others pointed out that, that the correlations that are persistent in thermal states are enough. So how should I think of the field in general? Because imaging is kind of a slightly different ball game than kind of metrology, right? I mean, so there is imaging, steganography, like there's a couple of different fields here which are kind of adjacent to each other. And do we want to generate large amounts of entanglement? Because there is also the super Beer's law issue, right? That the decoherence rates are higher. So how should I think about this field if I was just an outsider looking in?
Right. So, well, what Sai is pointing out, this quantum imaging as a field started almost like in 1995, I would say. I don't have those slides here. But yes, the status of the field, what you was referring to as ghost imaging or coincidence imaging and so on, there you utilize correlation in just one basis, let's say position basis or momentum basis. And that's why it turned out that whatever scheme utilizes correlation only one basis is bound to fail. I mean, you can have local hidden variable interpretation in one way, or you can have thermal light way of doing things. That can always be done. Whether it is done or not, it can always be done. Because at least you have to have some steering inequality as like that, or the EPR uncertainty or something. But if the correlation, even though you have entangled photon, you're utilizing correlation only one basis, and that's why it doesn't work. So now people have started looking at situations where you do require entanglement. That field is not, I would say, there yet. It will probably still take a while. Have a complete entanglement-based imaging.
There was some suggestion that signal-to-noise ratios are better, right, with entangled photons?
Yes, so that again, I don't have that here. When you go very low, but I mean, whether that can come up to some practical use, that is still, needs to be seen. But sub-short noise part, yes, that people have been able to use and say there is a quantum advantage, at least for the sub-short noise part. Yes, that is correct.
Okay, thank you.